Okay, so I wanted to illustrate a problem. That problem is a flat Earth logical inconsistency that anybody can verify, and you use reality to do so. You do not need a CG map and or continents, layouts, or anything like that. There are only a few things that you need to know. One is that if we do choose Australia, that there are places in Australia below this dotted red line, because this dotted red line is actually the Tropic of Capricorn. Now, Brisbane sits below that ever so slightly, and then much further below that, further away from this tropic, is Hobart in Tasmania. Now, I want to concentrate on one specific day, not a range of days, not a year, one day. Let's narrow it down, December the 21st. So now, what I want to do is have a look at these rings. These rings symbolize, or outline rather, and we only need this one for now, the Tropic of Capricorn. So in reality, it's very easy to go to Australia and know and verify that on this red line at zenith, the Tropic of Capricorn allows the sun to be directly above you. Wicked, amazing, fantastic. And that if you move further south, you're moving predominantly further away. The closest you can ever get is directly underneath. If you move south, you're moving further away. Very important. So let's have a quick look at that. So we can see that Brisbane, which is here, and Hobart, we can see that Brisbane is closer predominantly. It could be closer, it could be directly on the red line, but it's closest to the sun on the Tropic of Capricorn. And Hobart certainly isn't. Now, there's another one over here, and that's Finland. Now, believe it or not, if you work out just from the proximity of this circle, what's predominantly closer on average, you'll find that Finland is actually closer to the sun than these two being on the line. It's pretty cool, actually. These are all, you can verify these, but let's just concentrate on these two for the moment. So these two for the moment. What we've got here is we've got Australia, sunrise, sunset, and we've got Brisbane. Now, if we go to Brisbane and we go to December and we go to the 21st, bear in mind the difference between Brisbane and Hobart, there is actually a 1 hour time zone difference, I believe. But all of that is irrelevant. All we need to worry about is on the 21st, how long is the day? And the day is 13 hours and 52 minutes. This is verifiable. This is from sunrise to sunset. And it's 13 hours and 52. In Brisbane, this red arrow that is here. So this red arrow, Brisbane, we can see quite clearly on time and date that no one's ever invalidated that it is in fact on the 21st, 13 hours and 52 minutes long, the day between sunrise and sunset. Awesome. Glad we got there. Now let's go to the one that's further away, shall we? The Hobart example. So here we have Hobart, which is in Tasmania. And then we'll go down and we'll go to December, and then we'll go to the 21st. And then we'll have a look at the day. Look, what the hell is up with this day length? 15 hours and 21 minutes. Now, this is a bit weird. That means from sunrise to sunset, you can see the sun longer than you can in Brisbane. But how's that work? So on this blue line here, moving further away predominantly from the distance to the sun, I can see the sun for longer. How's that work on a flat Earth? But wait a second. So now let's go back and let's have a look at one other place. Let's have a look at Finland on the same day, on the 21st. Now, I've chosen a small town in the center of Finland. Look at what we get here. The day length is 4 hours and 26. So the sun above the horizon is, whoa, it's not that great. It's very low to the horizon as well. Wow, that's not a lot of daylight. Not a lot of daylight at all. Now, if we go back over here and have a look at this. So this green here, which is in the center of Finland, which is predominantly closer to the pink circle most of the time, for some reason, could only see a very small portion of this circle for a very small apparent amount of time, less than 5 hours. Yet here on the outside of the circle, you can see it for 15 hours. But then if you get closer, you can only see it for 13 hours. Seems to be that the closer you get to the center, the more irrational this becomes. So anyway, now that we've got this obvious issue, shall we try and special plead it into existence with Dome of Vision, something that can't be demonstrated or is made of that much math and projection that when you work out the source code to Walter Bislin's, you realize the starting point is observations on a globe, going through many coordinate and mathematical translations, including lookup tables, including heavy mathematics to work out how it would have to be on a globe, using magic math. Yep, we could magic this into existence, only solve direction of the sun and elevation, not the size, mind you. But it can be solved, this one simple aspect, by introducing all manner of things and saying it just works with no demonstrable evidence for that being the case. Or could it be that there's another answer? So, what about if we were on a 6.2 million meter radius sphere or thereabouts with a 23.5 degree axial tilt towards a very, very distant star that we call the sun? What about if all of the land masses, including you and I, are on this sphere? And what about if it's rotating? Just floating through space, rotating to a very distant 93 million mile away sun. What would happen then? Well, turns out if we were on this magic space ball, flying through the sky and it just rotating at the size and angle they say it is, at the distance they say it is, pretty much matches time and date and reality for anybody. Weird, right? So let's just verify this. So I've got 2 locations in Australia. Well, and obviously Tasmania. So on the top right here, we have a red pin in Brisbane, a blue pin in Tasmania, Hobart. So we can see that Hangabout, yep, it crosses just like so. So we can, Brisbane crosses, we can say they cross at the same time. But we know that Hangabout, Tasmania, is further away from the Tropic of Capricorn. So how does this work? Turns out the angle of rotation on a sphere matches reality perfectly, because we can now see that Brisbane's day has ended. And only a little bit later, in fact, a couple of hours later, an hour and a bit later, does Tasmania's day end. Interesting that this works on a sphere, right? And it works anywhere on this sphere, for any day, for any prediction that just matches by nature of rotating it. No magic and no special pleading. And guess what? You know, that really weird thing where there wasn't a lot of daylight in Finland? Guess what? That works too. It's the green arrow. And look, their day, not a lot of day, their night. Job done. How weird is that? If you're on a sphere and it's rotating, all the predictions that you can get from a sphere that's simply rotating from a distant sun match reality outside, including time and date, whereas everything on a flat Earth is logically inconsistent. I would love an explanation of this with demonstrable evidence, not special pleading, not magic, not, hey, look at this thing that I don't understand because it's heavily coordinate transformed and mathematics, like Walter Bislin's Dome of Vision, which isn't a dome of vision. It's a magic make-believe dome that was a piss take to flat earthers to say, hey, look, this can't happen. This is the amount of maths needed to make your stupid flat earth work. Whereas on a sphere, we just have to rotate it and be on it. How cool is that? I welcome anybody to comment on this and prove otherwise. Cheers.